protocol on which I'm working right now, call it RSocket. So in order to make this presentation really interesting and inspiring and entertainment, I don't like to explain some common things about the protocol and showing some boring things. I want to show you the power of RSocket by implementing the Pacman game. How many of you have ever heard about Pacman before or tried to play this game? Okay, so I hope you will enjoy this presentation because we will be playing in multiplayer Pacman today. Alright, so I would like to save your time and explain for whom this talk first, so you will be able to quickly switch the room and learn something more important for you. So this talk is for people who build networked application today. So if you are doing microservices, if you're building browser to or client to server application like browser, server, mobile server, this talk will be for you. We will see how you can apply this technology and get super high performance. So if you care about performance, this also will be for you. If you're building real-time games, I'm just curious, how many people are building some real-time application here? Okay, one person, great. This will be important for you as well. And this talk will be really useful for all reactive adopters. I'm just curious how many people are doing reactive programming on the daily basis or heard about that at least. Any reactive programmers? Okay, just a few, great. So this will be also useful for reactive adopters. Alright, if you're still with me, my name is Oleg, I'm from Kiev, from Ukraine. I work for a company called Netify, and also I really love reactive programming. This is my passion. I believe in this way of doing and building React software today. Also, I started maybe a few years ago contributing to Project Reactor, which is one of the implementation of reactive streams. And I wrote a book how you can use reactive programming with Sprint 5. Actually, I have this book with me, and for the most active participants of this talk, I will give away this book. So be active here. All right, let's talk a little bit of what we are going to do today. First of all, we will define the problem. We'll define what kind of application we are going to build. But first of all, we will focus on comparison and choosing the right protocol. For now, we will not go into deep detail of Pacman game business logic, and we will only focus on protocols because this is the most important, and we have to figure out which protocol is suitable for game development, for modern application development, for microservices application development. That's what we are going to do. Then we will have fun because we will play in the Pacman game, we will assess, and we will try to figure out which protocol is best and better by playing the real Pacman game. And finally, we will figure out what is the best protocol. Does it work for you? Are you ready? Okay, let's start. So first of all, let me explain the kind of what we are going to implement and what will be the multiplayer Pacman game requirement. First of all, we are going to build the browser client game, browser server game. So in case we have a server and we have a browser, the first call will be to a server in order to get the first HTML page. But since we will build the lightweight and modern browser game, we will return only an empty HTML page. Then we want to have kind of server-side push, and we want to get all the rest of the data asynchronously without any extra request from the client side. What else? Then we have to make a first interaction between client and server. For example, we have to send a nickname and get the state of the application. So we have to figure out what's going on in the map right now, or kind of register in the game. Then we have to somehow send our information or our state of the game from the client side to the browser. For example, we can send on every step, we can send information about location of the Pacman or the Ghost, so the server will be always aware of what's going on our map. This is the simplest and maybe the easiest implementation for the game, but this is fine for us. And of course, since we have client-side streaming from browser to server, we will have to listen to other players. So we have to listen to updates of other planes from the server to client, and in this way create some real-time gamers movement on the map. All right, along with that, we will have to have some challenge. in the game, because this is Pac-Man game. So every ghost should try to catch a Pac-Man, and every Pac-Man have to collect some items on the map, and in this way get the best score. That's what we are going to do. But as you can see, we have only game client and server interaction, some game business logic, and that's good. That could be a little bit boring for real enterprise developers. Thus, I prepared a small part related to real microservices. Thus, pay your attention. In our system, we have a real part of bloody enterprise, real enterprise system. So here we have Kafka. How many of you heard about Kafka before? All right, almost everyone. So Kafka in general is an elastic storage in which we are going to send information of every step, every movement of our Pac-Man on the map. So I'm spying for all you, and I will be collecting all of your behaviors and movements in order to make some data processing pipeline. So on every stage of my pipeline, I will be consuming messages from Kafka on the opposite side of the Kafka. Then we'll be sending all this data to intermediate processor in order to do some aggregation. And of course, I will try to feed this information to my final consumer in order to teach my bots how to play the game. Of course, this pipeline could work really fast, or it could work really slow, because we are living in a real world environment. So we don't know how fast our system are in the moment. So we have to be ready it's expected so that our system could work slowly or really fast. And we don't know at which moment it will work fast or slowly. So to summarize what we have in our game from the networking, from the communication perspective. First of all, we have server-side push, that's clear. We have plain request response when we exchanging our information like nickname and state of the game. We have client-side streaming when we are trying to send location information from browser to server, and we have some server-side streaming when we listening to the other players' updates from the server side. Along with that, we have machine learning pipeline which are teaching our bots to play, and our final subscriber in this pipeline can work really fast or slow, we don't know. But we have to preserve the stability of this pipeline in order to collect all important information. Does it make sense for you? Okay, so let's try to look at the toolkit that we are using right now in our application. First of all, on the backend side, we are using Spring 5. How many Spring 5 users do we have in audience? Okay, just a few. What else? What are you building right now? What frameworks do you use in order to build Enterprise? Spring 4? Okay, you have to migrate to Spring 5. That's easy. Don't worry. Okay, we are using Project Reactor. I believe in this technology. I believe in this project. So if you want to use reactive programming for high-performance server, use Project Reactor. This is really suitable for backend. This is like RxJava 2. So if you're familiar with RxJava, this is identical framework, but focus it on the backend stuff. And we are using protocol buffer. How many of you are familiar with protocol buffer? Okay, for those who don't know what is protocol buffer, this is messaging format. This is binary messaging format designed for high performance message exchange. So it allows you to kind of compress your data in a binary format and make your message as small as possible. That's about protocol buffer. And here, since we are building game, we will use this message format for message exchange. On the front-end side, just for your information, I'm using Phaser framework for all the browser kind of action writing and game development. Then I'm using Reactor.js because of the same reason as Project Reactor on the Java side. And I'm using TypeScript because I love TypeScript. I don't like JavaScript with its dynamic typing, and I really love TypeScript with proper strong typing on my browser side. Finally, I'm using protocol buffer for the balance between client and server, and that's basically what we have in our application. So let me show you quickly. This is the source code to our app. If you're curious, if you want to double check that I'm showing exactly what you see on the screen, just follow the link on this QR code and you will see the same sources. So Let me quickly scroll to my app. Do you see it well? Can you recognize what's going on the screen? Okay, let me open some, for example, some code. Do you see it on what's going on the left side? Okay, great. So what do we have here? We have a few components here. We have a game client. This is browser part, TypeScript only application. And then we have some game servers. This is basically our Spring Boot app and main game engine, plain Spring Boot application. I guess everyone in this room saw something similar or wrote the same application before. And we have a plain structure of our app. So this is basically a three-tier application. We have services, repositories, controllers, and we have some business logic implementation. Really plain, everyday application. So we have, of course, an API definition over protobufs. That's what we have here, like protofiles for our DTOs and messages. And yeah, we have our part of our messaging pipeline. Of course, I don't have the whole application right now. I have only the part related to the demo. So we have, of course, some service that collects metrics here. All right, let me go back to the slides. And now, once we saw our application, this is really plain Spring Boot application, we have to figure out what kind of protocol can we use in order to finally implement our game. So, what do we have today? Do you have any idea what kind of protocol can we use for our app? Yes, right. We can use HTTP1, for example, because HTTP1 is the most common protocol for our days. Everyone is using HTTP1, right? We are building services and client-server communication, so we're most probably using HTTP. What else do we have? gRPC, this is framework, so we will be back to that. But from protocol perspective, what do we have else? What else do we have? Yeah, for example, we have TCP. This is a really proven protocol for building real-time games, and it's used for real game servers. So we can use this protocol, right? What else do we have? UDP, can we use UDP on the browser side? No, yeah, that's why we have to skip it. What else? Maybe HTTP2? Can we use it? Yeah, most probably we can use it, because HTTP2 is a modern, more advanced HTTP1 upgrade, so it provides only one connection, and we have to use it, of course. I'm not sure that we can use something else, so we have to work with this stack of technologies. But I have a question. Can we use TCP from browser to server? No, we can't, right? We can't use TCP on the browser-server communication. And most probably we have to take a look at WebSocket, right? Because WebSocket is almost the same TCP. So we will be using HTTP2 for comparison, WebSocket, and HTTP2. And now the next question. How we can compare all of these protocols? From my point of view, first of all, we have to focus on maintainability of every protocol. We have to focus on how many frameworks support this technology, what size of the community of this particular technology, and how large is the adoption of particular technology. This is important from the development experience side. On the other hand, the more important is stability, because our application should just use, and it should just take everything possible from the protocol. So protocol have to provide lots of guarantees in order to make our life easier, right? Does it make sense? Yeah. And finally, the most important for our case is performance, because our application should work fast. It should provide real-time data from between clients, so we will be able to play normal games without lags, right? So that's what we will choose, we will take into account during the comparison. And now let's take a look at old HTTP1. Of course, this old HTTP1 is obviously not that good, but we have to give a respect for this technology. So why HTTP1, for example? Because HTTP1 is plain and simple. It's used for many, many years, but by many different languages. So you can find the HTTP client and HTTP server implementation, any languages, any framework today. That's why it's really cool. Why not HTTP? First of all, because it's text-based protocol, right? Every time you want to send something, we have to encode everything in text. On the one hand, it's good. On the other, it's not fast. In turn, we have inefficient resource usage because HTTP1 approximately create more than one connection. In one browser it could be 8, in another it could be 10, and we don't know how many connections will be used in order to create plain client-side, server-side communication in our applications. That's why our server will have to handle more connection than expected from one client. And that's not good because this leads to slow performance. And this is really not good for us. Finally, we have some communication rigidity because in fact, HTTP1 from the browser perspective supports only request-response communication. So in order to send, for example, client-side streaming, we have to always send a client kind of request-response communication type. We have send request and response, request and response. Of course, there is a few hacks like half-duplex connection from the server to client, which is called server-sent events. So we'll be able to observe some server-side streams, but this still is not really good solution for us. We have to have a proper end-to-end, all type of communication support. So, finally, HTTP1 is not resilient, which is absolutely unacceptable for us. HTTP1 from this picture could look like this. So, and on the left hand is obviously our server. So HTTP1 just sending data. And we don't have an option to say, okay, don't send me, just send me a few requests per second and not more. Of course, there is a few hacks on that, but we still don't know for sure how many requests our server can handle at a moment in time. Zeus, we have to implement lots of hacks and provide lots of frameworks in order to handle different cases, like we have to provide retry logic, timeouts because we don't know for sure that our request will be processed. So we have to handle lots of problems and provide lots of solutions for that. And this is another problem that impact our development experience. So it's clear. We need backpressure, right? How many of you knows what backpressure means? Okay, just a few hands. I will show you a real-time demo of backpressure. So please, Irina, can you help me a little bit in order to show how backpressure works? So we will try to play a real plain game. So Irina will be throwing to me candies, and I will say, okay, I'm ready. Once I will be ready, I'll start catching all these candies. At least I'll try to catch them. Okay, so let's start. I'm ready, throwing as much as possible. Okay, so as you can see, okay, so that's what can happen when I got too many candies in my hand. So that the same could happen with your servers, and you can just imagine how many requests could be dropped and how many exercises you have to do in order to resolve all these dropped messages. And now I'm going to show you the real backpressure. So now I want to have one volunteer or a few volunteers from the room who want to try to be part of this backpressure show. One hand on the back. So now what you have to do, you have to say how many candies you are ready to catch. Say it to me. How many? 0. Okay, no, 0 doesn't work. 1 or 2 or 3. 3. Okay, so I'm ready to handle 2 candies. Please, Irina, throw me 2 candies. Okay, so now I will show you. I will try to throw. Sorry. I'll try to throw again. So in this way, as you can see, I will ask only the same number of candies as this guy at the back asked me as well. And in this way, the backpressure was controlled because I know for sure how many candies he is ready to handle and how many candies I'm ready to handle as well. So I will ask not more than this number of candies, and that's why producer won't overflow me by candies as it was at the beginning. So did you understand how backpressure works and why it's important? So great. Let's move forward. Now we understand that HTTP1 doesn't work for us, so we have to use a little bit different technology. So what else do we have? We have WebSocket and HTTP2. So let's start with WebSocket, for example. Why WebSocket? Basically because this is almost the same TCP with no overhead. WebSocket just gives a little bit of framework to the same TCP connection, so it's almost the same. And this WebSocket is designed for high performance between browser and server communication. That's why it's cool. Why not WebSocket? First of all, this is really complex technology from the developer perspective. At least when you start using Spring 5 and when you try to create a WebFlux API with WebSocket, you will get lots of pain. That basically was my experience of building WebSocket API using Spring 5 and WebFlux and WebSocket. In general, this is really complex, and at the end, you will get your own application protocol on top of WebSocket because you will have to define routing, you will have to define message format, etc., and so on and so forth. So you have to build everything yourself, and of course you will experience and you will face lots of bugs and problems. This is not good. Of course, today we have lots of existing solutions for that purpose, like Sox.js or Socket.io. So, for example, we can try to use Socket.io because this is a really popular framework on the browser server communication in the JS world. So let's try to use it. And now let's try to figure out whether it's good or not by scanning this link and trying to play the real Pac-Man game using Socket.io. So let's do that. And let's find out whether it's good or not. I'm encourage everyone to follow this link because it will be fun to play the game. I'll give you a few more seconds to scan the link. And you will see the plain browser application. You would have to enter your nickname, make the scroll up in order to hide your bar in the browser, and then you will be able to play the game. It will take a little bit of time to connect to the game, but this is fine. So let me go to Socket.io. Let me reload it. Yeah, it works. And let me log in. So here we go. Here we go. It seems like it works. So let me find someone and try to catch it. Whoa, something went wrong. Why? So let me try again. And whoa, what's going on? This is not good. Do you see those flags? Oh, again, I missed everyone. This is not good. It doesn't work reliable. Oh, I missed everyone on the screen again. Again, it works and it don't work at the same time. So this is not good. This is a bad part of Socket.io. So we don't have a stable latency, etc. And this is not related to network because I have Ethernet connection here. This is about Socket.io on Java. Yeah, so let's go back to our session. And as you saw, the latency is not good and the game experience isn't good. Do you agree with that? Yeah, the game experience is not good at using that solution. What about development experience? If we're going to look at the Spring integration with Socket.io, we won't find anything because there is no integration with Spring, and we have to make this integration ourselves. So we have to start the server, and we have to take care that server will end once our application goes down. So we have to make this by our hand. On the other hand, the whole implementation of Socket.io server on the Java side is basically a copy-paste of not Socket.io server. So if we are going to look at the code, we will see the lots of callback implementation of our API. And this is not good because in normal development on the Java side for normal Java enterprise solution, we are using absolutely different technique for data processing. And this is not good from development perspective. And finally, there is no direct access to Bytebooth. In fact, Socket.io server for Java is built on top of Netty. How many of you heard about Netty before? Okay, just a few hands. And the most important part of Netty is Bytebooth because they allows us to use efficient memory. It provides efficient memory usage by ref counting, by storing all the data, all the bytes outside of heaps, so we decrease the time spent on GC a lot. So it's really important technique in Netty. In fact, Socket.io for Java does not provide us direct access to Bytebooth, and every time we have to take everything to heap and work with heap data. And this is more even kind of cruel in Socket.io. That's not good. So the question where is good? Where is this technology is pretty good. In case you are a pure JavaScript developer, in case you are using Node.js, it's really good technology. In fact, in Java, it's really slow, first of all, and the development experience is really bad. So it doesn't work for us. So what else can we use today? Any ideas? I heard one person told me about gRPC. So can we use, for example, gRPC today in order to build our game server, in order to build our web multiplayer Pac-Man game? How do you think? I think we can. So let's try to figure out whether gRPC implementation will be better. Because gRPC uses only one HTTP2 connection, so it should provide much better experience, right? Let's scan it and figure out whether it works better or not. Okay, let me go and take a look at gRPC implementation. Here we go. Now we are looking at gRPC, and let's play. Okay, we are far from anyone again, but we will hope that it will be better. At least I'm eating some items, so let me find someone here. Where is everyone? Come on. Oh, I see someone. Okay, let me eat. Okay, someone. Okay, yeah, I forgot that I'm not a ghost. Let me try again. Oh, yeah, the latency is better. It's still not the best, but it's much better than Socket.io. Do you agree with that? We almost don't see any lag so far. It works almost smoothly with small latency, but it's better than before, right? So it's better. Let's go back to our slides. And so why we should use gRPC, for example? First of all, it's built on top of HTTP2. So it provides only one connection. It guarantees that everything will be multiplexed through one connection, and we will have only one connection used during the whole client-server communication. On the other hand, it provides good development experience because it provides end-to-end integration with Protobuf. I will show you about which integration I'm talking about. First of all, when you try to, once you start using gRPC, for example, in Java, you will get a proper plugin for Maven and Gradle. And this plugin will allow you to use all of these proto files, which we define here. It allows you to use all these services, define it as an API for your application. So here we have a game server which says, okay, this is request response. And here we have a player service which says, okay, I want to send you a stream of location and get one response once my stream is done. And here is a server-side streaming where I get a stream of players information in order to update the location of all players on the map. And all of this is defined in this API. And then using this plugin in Gradle, I will get this beautiful code, this beautiful kind of DTOs generated. And I will be able to use this in order to build my API and my controllers in my game server like this. I'm going to show you in a sec. So this is really good development experience because there is integration with Sprint, so I can say, okay, this is my gRPC service and everything will be working fine. This is cool. And that's why we have to use gRPC, because of good integration, high performance, etc. But the next question, why not gRPC? How do you think? Okay, there is no idea. I will help you to explain that. First of all, because of this. Who sees what the problem is here? Sorry? It's not. I will show you. We are sending too many location requests. Do you see it?
We don't have understanding what exactly we're sending and the data which is inside.
It's not that problem. I will show you. So the problem is that we are doing the plain post request, the plain HTTP on the browser side. And we are doing, and this is real gRPC, this is gRPC web, and gRPC is a fake. In fact, gRPC web works like this. We have a proxy in between, which accepts our plain HTTP1 calls. So we are creating additional connections because there is no guarantee about HTTP2, so we can fall back to HTTP1. And then this proxy in between will transform all these calls to normal gRPC calls. In fact, in order to listen for streaming, we have to create another connections, continuous connections in order to listen for updates. So again, the same problem as with HTTP1, we have too many connections open, we have only text-based protocol, and this is official solution for gRPC browser integration. You can double check that, but this is official solution from Google. And this is not good. But it's fine, it's worked with some latency, but it could be acceptable. So let's try to figure out whether gRPC is stable, and it can take the stress test from us. What is the most important from the gRPC side? gRPC team says that we have back pressure. And if we are going to take at the API of gRPC, we will see something like this on the subscriber side, and we will see the proper call of how many elements do we want to get, right? So it looks like how we demonstrated it before, where we have the proper sending of how many candies do we want to handle right now, right? So this is something similar. However, if you're going to look at the publisher side, we will see something like this. Do you see a problem here? I'll show you. So if you're going to look at this point, we will see some conditional checking. So this is basically a volatile field, which is called is ready. So it's volatile boolean under the hood. And the problem here is that we can't have erasing, because we can't know for sure that at this particular moment, once we check that is ready is true, the next moment it won't be true, it could be false. So we don't know for sure that the next call to an X will be absolutely correct in terms of back pressure control. Even so, a few days ago, I noticed a real issue and real complaining from real person on GitHub. So this is a screen from GitHub from OpenNet issue, still OpenNet issue from 2016 about simplification of back pressure. And the main maintainer of gRPC Java says, okay, so the person was complaining, real person was complaining that there is a race condition when the server tries to check the isReady field. And the author and the maintainer of gRPC Java says, okay, this seems totally fine, there is a racing, and gRPC can't handle this and can't prevent this racing, it's fine. And the only guarantee that gRPC provides to us in case of isReady field checking, that in case it returns false, there is no other guarantee that this false will be observed by our application at the next moment. And this is really shit. So we can do something like this and say, okay, the end of gRPC. So to summarize, in case we have a publisher which can overproduce one element, this is fine. But what if we have more than one publisher, for example, in one Java application, and every publisher overproduce one element? So what could happen? I'm going to show you. I created a scenario in our system, so this will be a part of our test of our system stability. However, instead of Kafka, we will be using some fake data generation because it will be hard to reproduce everything with real Kafka. So we will be using part of Project Reactor, which guarantees that every call to this inner function will happen only if subscriber shown its intent to receive some messages. So once the request method has called with, for example, 5 elements, this function will be invoked only 5 times, and we will produce only 5 fake data metrics. So how we are going to test this, our pipeline, and how we are going to figure out whether gRPC is stable or not. We will try to make really fast subscriber at the beginning, because this is fine, this is how the system works usually. And then we will try to decrease the stability of or make the slow subscriber the next moment after the fast, and we will figure out whether the whole pipeline will be able to survive, and whether this guy at the middle will be able to handle all these messages, right? Or die. In order to make it more real to what we have in cloud, because in cloud containers, we provide only a few gigs of memory, right? We provide only 2 gigabytes or 4 gigabytes to our container application, which is running on Kubernetes, for example, or inside the Docker. So we are going to provide the same environment for our local test. We will give only 1 gig of heap and only 1 gig of direct memory. Does it make sense for this test? Yes, it does. So let's figure out whether it works or not. And what do we have here? So this is what's going on right now. Here on the right side, we have our game server. On the bottom right side, we have metric server. So here is game server. Do you see it? And here is the metric server. So the final subscriber in our system. So we have some more elements. We have visual VM in order to figure out what's the state. And we have some information on the metric side. We have our dashboard, which allows us to control the speed of our subscriber, so we can make our subscriber slow, and you will see short, less messages requested from the subscriber. And now we returned everything back, and now we have more messages from the subscriber requested from the subscriber side. It looks stable. Our metrics says that everything is fine. So let's run the test. Here is exactly the same code you saw. Here is our producer, which generate metrics, fake metrics. Here our integration with gRPC, we create a connection with OpenNeti channel on particular port, and then we are using our client here. So this is basically it. We're producing some messages, and it just works. So now we are going to run this up. Let me run it. And we will see the new connections to our final subscriber on the screen. So we will make our subscriber really fast, and yeah, we can see we can observe new connections on the screen. So we got a few more subscribers. The state of the system looks pretty good, so there is no incident so far, so it just works. We will see a throughput scrubs in a moment, so we will see the throughput of gRPC. Yeah, it's about 150K of messages per second, really fast. So gRPC looks good. So let's make this up slow. Let's make our subscriber really slow in order to figure out whether backpressure will be able to prevent the crash of our system in gRPC. So let's submit less request size. So we made our subscriber slow. Do you see there is no messages requested from our publisher, but it still works. And let's take a look at the metrics. So the throughput going down, it's going down, which is a fact that backpressure works somehow in gRPC. But wait, what's going on? This is my direct memory pool. Shit, it's not good. I have only 1 gig. Oh no. Oh no. We are out of direct memory. And yeah, it looks like it works. So it works, or it doesn't. We have to figure out that. Nah. What is this error? Oh no. Okay. It was a video. Sorry. I knew what should happen. I'll show you again, because this was a real recording of demo, because my machine is about 67 degrees, so it's overheated. You can see that in general. That's why I recorded everything, and in fact the end of this show is out of memory, and this is a problem. So what happened basically? What happened during this demo? First of all, everything was fine. We got a pretty good throughput at the very beginning, so the state of the system and the state of our producer and our subscriber was the same. We got absolutely same throughput on the both sides. At the next moment, what we can see, that producer produces a little bit more messages that our consumer consumes. Do you see that? Do you see this gap? This gap is about 20K of messages. In the next moment, we have again the same, almost the same gap, a little bit less messages stored somewhere, but we have this gap. So producer produces more messages the consumer consumes. So what it leads to? It leads to this problem, which leads to this. Because in general, everything is stored somewhere. It's stored in our direct memory. And of course, in case our subscriber gets too slow suddenly, we can get memory overflow because of this recent problem. So, if we're going to look at gRPC backpressure, we will see something like this. There is backpressure between subscriber and another subscriber. However, there is backpressure, the same backpressure between our producer services and our middle service, but we don't have real backpressure between this guy and those guys. So we don't have real end-to-end backpressure that I have demonstrated at the middle of the presentation. And this is a problem. So we can say, okay, gRPC have backpressure, but it's not real what we want to have here. And you can believe me, because I did all possible from my side in order to make reactive gRPC, which is used here, a proper solution. I spent lots of time to improve this solution in good sense, but again, I can't do anything in order to make gRPC real stable, even with reactive streams. So, to summarize what we have seen, everything is slow or hard to implement like Socket.io, or lack of browser support like gRPC. Every technology does the best effort in order to implement proper flow control, but it's not good. It's just a hoax. And do we want to spend our time in order to solve all of these problems, in order to find a proper solution for all of these cases? The same question was asked at Netflix 3 years ago. Because Netflix is basically a company focused on the streaming. They created RxJava, they provided the most modern technology we are using today. So this is a real company which is doing real cutting-edge things. And in their cases, they have almost the same situation, but in their case, they have lots of services to which connected lots of clients like mobile clients, computers, PlayStations, and we don't know what is the performance of those clients. We just have to stream the stream of data through gateway, for example, to those clients. And just imagine what can happen once those clients became unavailable or really slow. Everything can just go down. And this is not a good case. That's what was observed at Netflix 3 years ago when they tried to use gRPC in production. That's what they observed. And you can listen to a real interview from one of ex-Netflix Edge platform developers, which is explaining what happened in their environment. I recommend you to listen and to ensure that they're explaining the same things. So, what they did, since they're cutting-edge company which is building proper solution and newest technologies, they decided to create own reactive streams protocol that got a name RSocket. So now we are going to look at RSocket way and figure out why it's better. So why RSocket? What is RSocket first of all? RSocket is a good future, as for me, because RSocket solves all of previous problem. For example, it's binary protocol. If we want to send our Pacman, we have to convert our Pacman to binary Pacman, send through the network, and of course, protocol will take care of sending all the bytes, so we will be able to decode our Pacman back. In turn, it multiplex protocol, so we don't have to create as many connections as we have logical stream. We have to create only one and multiplex all the data through this one connection. In turn, RSocket will take care of creating a proper logical stream on the network layer and provide mapping of your messages and this stream ID. So the opposite side will be able to figure out to which proper logical stream this message relates. This is amazing. In turn, what you have to do, for example, in RSocket Java, you have to just use project reactor in order to send everything forth and back. This is bidirectional protocol. Why it's great? Because at the very beginning, you have two-wire connection, and at this point, there is client and server. After this point, there is only peers, because both can implement event handler, and every party and every peer can send a request and get a response back. What else? This is reactive streams protocol, and along with reactive streams manner and fashion, it provides back pressure support. So now, in order to handle back pressure, when we send a request and when we have a request and call from the requester side, this call will be converted to real frame and sent to opposite side, to responder side, and then our producer will be able to produce only the end messages we need and not more. This is really important. So we have real transmission of request and method call from one application to another between microservices over the network. What else? It provides not only streaming communication model, it provides lots of different communication model in order to handle all possible cases in real development. For example, request response. We can use request response communication with our socket. Or we can use advanced request response like fire and forget in case we just want to send messages and don't want to for response. For example, efficient log sending. We don't care about whether it delivered or not. We just care that we have sent it. There is request stream, so we can say, give me a stream of messages, server or responder, and it will give you. Or, for example, we can say or create client-side streaming by streaming messages to our responder and receive, for example, a stream of messages back. This is amazing. In fact, all of this feature could be used on absolutely different transports. There is a transport agnostic protocol. This is a transport agnostic protocol, so you can build it on top of, so you can use, for example, transport like a TCP, you can use WebSocket, you can use HTTP2, or for example, you can implement your own quick transport for RSocket application protocol, or for example, you can use advanced UDP like Aeron. This is cool. What else? There is a few more notable features like Lizin, which allows you to avoid circuit breakers, because now server can say how many requests you can do per second. And you have to follow this requirement, and you will be able to create only n requests and create n streams per provided period of time. It provides resumability. For example, if your clients are mobile phones, and what happens with mobile phones, we are usually switching different Wi-Fi's, we are switching, for example, network connection, and we can lose our stream. And in order to avoid recreation of the whole stream, there is resumability, which allows you to send a session ID, and then everything will be continued in case of network disruption or something like that. This is an amazing feature. And finally, there is fragmentation. So in case you have to send huge kind of messages like PDF files or videos parts, you can use fragmentation in order to split your payload on smaller chunks and send everything one by one when the network is available. This is good. This allows you to avoid any traffic overwhelming. Okay, in case we are going to look at this whole RSocket environment and ecosystem, we will see that RSocket is there is a few builds for different languages like Java, JavaScript, C++, Kotlin, or .NET. Right now we support .NET as well. You can use any architecture you want. For example, there is RSocket RPC as well. You can use Sprint messaging, which has integration with RSocket. You can use any message format, and you can use any transport you want. This is really cool. So let's try to evaluate RSocket in this case in multiplayer game. So I'm encouraging you right now to try playing Pac-Man, because now you will be able to, the most active gamer, for example, with the highest score will be able to win this book. So if you want a book about reactive programming in Sprint, just play, collect the most points, or eat as many Pac-Mans as you can and win this book. And let me go to RSocket implementation as well and see whether it's better or not with you. So here we go, here we're playing. Now let's try to find any players here. All right, where is everyone? Do you need a link to this game? Oh, okay. So, yeah, here we go. Here's the link. So, what is your game experience? Is it better right now? Is it playing kind of, is the gameplay is smoother right now? What do you think? Okay, let's go out. Yeah, it looks better. There is almost no delay. Of course, we have some network latency, but it looks better. So let me try to catch some Pac-Man. Here we go. Here we go. I'm the best player. Okay, it looks better, right? So almost there is no latency. It just works. I like it. What about stress test? While you are still playing, I'm going to run the same test right now. So what do we have? On the right hand, we have the same game server. So this is a game server with the same setup as before, do you see? 1 gig for heap, 1 gig for direct memory, so I'm running this up right now. And I'm running the same metric server. So the metric server will start in a sec. Yeah, it's starting. Yeah, it's connected, boss. Application has connected, and I'm going to connect to my game server in order to figure out what's going on from the metrics perspective. At the same time, I'm going to run a Docker and run chronograph and InfluxDB in order to collect some metrics. So here we go. And here is our control panel. So it works. Let's take a look at our dashboard. So let's take a look. Let's make it bigger. So in a sec we will see the result of performance collecting from our apps. So let's make our app or our subscriber really fast. Let's do the same trick. So now we are requesting about 500 keys of messages. So this is, oh no, yeah, this is a request size, and now I'm going to run our dosers. So here I have our socket doser. Come on, where is my RSocket? What's going on? I have to run a cooler. Again, this happened. Yeah. Here is my no gRPC doser. RSocket doser. Yes, that's what I'm looking for. Let me stop it first, and let me show you what's going on. The same setup, the same data producer or publisher, the same way of creation of connection to my server, and here is the same code for the client. So let me just run it. If we are going to compare this code with gRPC one, we will see. Oh, come on. Let's just run it. If you're going to copy this guy and compare with gRPC doser, just for curiosity, we will see absolutely identical code or almost identical code. So let me just, yeah, almost the same solution. The only difference is between how we create a connection to a server, but the rest of the stuff is absolutely the same. All right. So what's going on? We got a few more connections. So we will see some throughput. Yeah, there is some information about throughput. We will see higher in a sec. Yeah, it works. What about stability of our system? Memory works pretty good. Yeah, so let me increase this guy. Yeah, the memory is stable, only 200 of megabytes. The direct memory is pretty good as well, so it works. Produces some messages. Let's wait a sec.
I'm sorry, but unfortunately your time is running out, and we got a message from the organizers that the audience should get going to the iSense for the closing keynote.
Okay, so let me finalize it, and
Yes.
everyone will be able to go.
Yeah, wrap it up.
So, As the result of this stress, everything will be fine. I have a video recorded, so I will share with you afterwards for those who curious. In general, if you're going to summarize everything about our socket, the main advantages is the same simplicity of development because we have integration with Spring and Spring messages and our socket RPC, which is a replacement for gRPC. The performance will be higher. For those who are interested in about our socket, I will show the result, kind of the performance result afterwards. And we have efficient resource usage because we have only one connection. Finally, we have really high flexibility because our socket RPC and our socket supports any type of communication models. However, along with that, we have some disadvantages. First of all, the main disadvantages is that's the fact that this framework is still under development. And for now, we have just a really small community. However, the community which stands behind our socket is really great. First of all, we have Facebook, which supports our socket, and our socket C++ and JS. We have my company, which committed to support all of clients and improve this protocol and all possible clients. And we have Pivotal, which also helps us in development. Recently, we got Alibaba, which also started developing our Socket Go client. So we are looking forward to get really huge community behind our socket. Finally, if you're going to compare everything, we will see something like this. But the final summary is the following. Each protocol has its own benefits. Of course, if you want to use Node.js, the best proper solution will be, I guess, Socket.io because this is the most stable one. Finally, gRPC provides really high performance, but resilience and back pressure and reactive in general is about stability. So in order to get really high performance and stable solution, you have to use RSocket. Finally, if you're looking to learn something more about RSocket, I'm welcoming you to community forum. You can ask whatever you want. There is a video channels which is explaining a little bit more about RSocket from the different perspective and from different companies. And finally, there is RSocket in Spring. So if you want to try to use RSocket with Spring, just follow this link. And if you want to use real enterprise solution and real enterprise RSocket, here is the link. Thank you for your attention. And yeah, who is the most active player right now in the game? Let me take a look at this. The final look. Okay, I lose the connection. So, Christiana. Who is Christiana? Okay, so you won a book. Yes, you are the only one, so you won the book.